Okay, it is high time we interpreted the coefficients. Let me remind you that the coefficients are also called weights, while the intercept, bias. These notions are useful because the weights show how we weigh a certain input. The closer they are to zero, the smaller the weight. And alternatively, the further away from zero, no matter if positive or negative, the bigger the weight of this feature. Note that this is something which is true for our model, but is not universally true. It holds only for models where all variables are of the same scale, such as the one we just built. There are coefficient values and standardized coefficient values. These standardized coefficients are basically the coefficient values of a regression where all variables have been standardized. Other packages and software include the standardized coefficients because they allow for a simple and easy-to-understand comparison between the variables. Since, in such cases, the features are standardized, they all have a variance of 1, or the same scale. And whenever the scale is standard, or the same that is, we can simply say, whichever weight is bigger, its corresponding feature is more important. For machine learning purposes and prediction in general, we usually standardize the variables, like we did now. For homework, you can try running the regression without standardizing the variables. You will quickly realize why we did not go about the problem in this way. Okay. Now, another notion we must emphasize is that whenever we are dealing with a logistic regression, the coefficients we are predicting are the so-called log odds. This is a consequence of the choice of model. Logistic regressions by default are nothing but a linear function, predicting log odds. These log odds are later transformed into zeros and ones. Let's make this clearer. Here's the logistic regression equation. Therefore, all the coefficients that we have refer to the log odds. So, to make them more interpretable, let's find the exponentials of these coefficients. I'll create a new series in our data frame called odds ratio. Odds ratio is the correct term for what we will get after we find the exponentials of the coefficients. It is equal to NP-EXP of summary table dot coefficient. This has added a new column to our table where we have the exponentials of the coefficients. Next, I'll sort the data frame using the sort values method. Sort values requires us to choose the appropriate column by which we want to sort the whole data frame. Logically, for us, this is the new column, odds ratio. Here's the result. By default, the coefficients are sorted in ascending order. In our case, the most important ones are at the bottom. I don't particularly like this, so let's add another argument. Ascending equals false. Rerunning the cell gives us the desired table. All coefficients sorted according to the relevance of the problem at hand. So, how can we interpret them? If a coefficient is around 0, or its odds ratio is close to 1, this means that the corresponding feature is not particularly important. The reasoning in terms of weights is that a weight of 0 implies that no matter the feature value, we will multiply it by 0, and the whole result will be 0. The meaning in terms of odds ratios is the following. For 1 unit change in the standardized feature, the odds increase by a multiple equal to the odds ratio. So, if the odds ratio is 1, then the odds don't change at all. For example, if the odds are 5 to 1 and the odds ratio is 2, we would say that for 1 unit change, the odds change from 5 to 1 to 10 to 1 because we multiply them by the odds ratio. Alternatively, if the odds ratio is 0.2, the odds would change to 1 to 1. When the odds ratio is 1, we don't have a change, as multiplication with the number 1 keeps things equal. This makes sense, as the odds ratio is 1 whenever the weight is 0. Okay, do we have weights like that? Yes, we do. The daily workload average weight is minus 0.03, so almost 0, and its odd ratio is 0.97, so almost 1. So this feature is almost useless for our model, and with or without it, the result would likely be the same. Do we have other variables that can fall into this category? Of course. Day of the week and distance to work. To be honest, this is a bit surprising to me. To justify my mistake in logic, this is the time to note that they may not necessarily be useless. A more accurate statement is that, given all features, these seem to be the ones that make no difference. We will keep the features for now, but consider dropping them later on. Alright, what else can we see? We've got the 4 reasons for absence, which are the most important predictors. When we were creating the dummies, the one we dropped was reason 0. Reason 0 represented a situation when a person was absent, but no particular reason was given. Therefore, the base model is the case when there is no reason, aka reason 0. From the coefficients, it seems that whenever a person has stated any reason, we have a much higher chance of getting excessive absence. A good question would be, how much bigger of a chance? Let's explore that in the next lesson. Thanks for watching.